continue our discussion on governor. Okay, you can see this diagram. This is the same diagram as you are seeing in my last two classes. Okay, you may feel that I haven't made any progress and the same thing, but this is a general governor and our whole discussion is going to be on this. Okay, this is the spindle axis, this is the upper arm, lower arm, this is the collar radius which is fixed to the spindle, and this is supposed to represent the sleeve, and I am considering only half of the governor and the other half exactly symmetric to this that I have not drawn. Exactly the same thing. Okay, some of these dimensions what we come across here, RCU, LU, LL, RCL and MS and MB. Okay, these things will remain independent of sleeve position. Whether the sleeve is here or whether the sleeve is here or whether the sleeve has gone down, and therefore it doesn't matter. These dimensions will remain same. But all other dimensions like alpha, beta, R, omega and H, they keep on changing and they depend upon what is the position of the sleeve. Okay, so instead of dealing with only the mathematical expressions analysis, so please do not forget what we are discussing. We are discussing governor. Governor is supposed to maintain a constant speed for the engine, and for that we have a centrifugal governor. Centrifugal governor, every centrifugal governor has a sleeve. The sleeve will occupy a constant position, fixed position, constant position, as long as the load on the engine is constant. The moment the engine speed changes, when does it happen? When the engine load changes, the engine speed changes, and similarly the spindle speed also changes, spindle speed of the governor changes, and the sleeve will occupy a new position. So that you don't forget. So here, so I assume that the load of the engine is constant, and therefore the spindle speed of the governor is also constant, and for that I have derived an expression for what is called as omega square is equal to, this is what I have written, G upon H into MB plus MS by 2 into 1 plus K divided by MB. This is what I have derived, and without considering the friction. I assume that the load on the engine is constant, and therefore the governor sleeve is in a constant position, and hence there is no question of friction coming into picture. And this speed, what we call it as the equilibrium speed. And the only modification I would like to make in this G, I would like to send it inside, and therefore I shall rewrite it. This omega square is equal to MB into G into MS into G divided by 2 into 1 plus K. A small modification I have made it, and this is what I call it as equilibrium speed. Okay, how here omega square, this expression gives you square of the equilibrium speed, and this is the expression to calculate what is called as equilibrium speed. Okay, so now I would like to bring this is whatever I have calculated. This is without friction. If I don't take friction into account, then what is the speed? This is what I would like to calculate. Now I would like to bring friction into picture. So whenever the two bodies are in physical contact, and if they are likely to have a relative motion, then the friction force comes into picture. So here, what are the two bodies which are in contact? The sleeve is one, the other one is the shaft, the spindle of the governor. Okay, the governor spindle and the governor sleeve, they are in contact with each other, and they have relative motion, and therefore the friction between the two is going to be there. And what is the effect of that? That I would like to bring. Okay, so friction, as you know. Okay, small revision, very small this thing. I don't want to go in detail about this. Okay, so imagine that there is one body and which is lying on another body. Okay, so now I would like to move this. Okay, So for an imaginary situation, imagine that there is no friction. This is body number 1 and so this is body number 2. I would like to move this body 1 over 2. Okay. So for a while you imagine that there is no friction between the two. Okay. It is a highly theoretical case and such a real thing, such a thing will not be there. Okay, so whatever the care you may take and you may try to reduce the coefficient of friction, but you cannot make it 0. But an ideal case, imaginary case, I am assuming the friction between 1 and 2 is 0. Even if I apply 1 Newton force, then immediately it will start moving in that case. If the friction is not there, then whatever the little small fractional force you apply, the body will start moving. But if there is a friction between 1 and 2, that depends upon so many other factors, and let me assume that mu is the coefficient of friction between 1 and 2. So mu multiplied by the normal reaction between 1 and 2, that will give you what is the friction force. Friction force is equal to mu multiplied by normal, and this is the maximum friction force. The maximum friction force is equal to mu into N. Now, if I apply very small force, say 1 Newton apply, then this body will not move. Why it doesn't move? Because when you apply force, this body feels like moving towards right. But when it feels, then immediately the friction force will come into picture and that force will act in the opposite direction. Okay, this force, unless you apply a force which will overcome this force, then only it will start moving. Okay, therefore, whenever a body feels like moving in a direction, then exactly opposite to that we have a friction force. That is very, very important. Okay, so let me make use of this concept now and in our analysis, and let me assume now. So only if I overcome that friction force, then only it will start moving. So now let me assume here. Now I would like to take friction force. Let Fr be the friction force, the maximum friction force between what is called as the sleeve and the spindle. Okay, so now this friction force, what is the direction of this friction force? That depends upon in what direction the sleeve wants to move. Okay, now I assume that in this diagram, whatever I have drawn, I assume that sleeve is neither in the bottommost position nor in the topmost position, somewhere in between. Okay, I assume that is why I shall take this omega as the speed here. Okay, little later, if the sleeve is at the bottommost position, then I shall have slightly different set of notations that I shall explain you. And similarly, if the sleeve is at the topmost position, then what are the notations? That also I shall explain you. I shall assume that the sleeve is at neither at the bottommost position nor at the topmost position and somewhere in between. Okay, now the sleeve wants to go down. Okay, I assume that I have a case sleeve wants to go down. So wants to, this is in general, and the technical term we say tends to, sleeve tends to go down. Sleeve tends to go down. Okay, how does it? So why the sleeve tends to go down? Because the load has decreased. The load has decreased, and therefore the speed has increased, and we are supposed to move this speed as so load has increased, the speed has decreased. Okay, therefore the speed also has decreased here. When the speed goes down, then the balls tend to move inwards and the sleeve comes downwards. The sleeve wants to come downwards. Okay, so sleeve tends to go down. So when the sleeve tends to go down, what will be the direction of the friction force? Friction force will act in a direction opposite to the tendency of movement of the sleeve. The sleeve wants to go down and therefore the friction force wants to go up. The friction force will be acting in the opposite direction, that is upward direction. So therefore, so now I would like to show what are the forces that are acting here. So what are the forces now at this instant? Now I have not only Ms into G, I also have what called the friction force. The friction force is in the upward direction and Ms into G is in the downward direction, and therefore the net force in the downward direction is equal to Ms into G in minus Fr divided by 2. Why divided by 2? Because I am considering only half of it. And this all other forces remain same, mv into g, and here it is mv. Please remember the speed is not omega now, and I shall assume that it is omega dash square into r, because there is change in load and that is why the sleeve wants to move, and the new speed is omega dash, and therefore the corresponding centrifugal force is mv into omega dash square into r. Okay, so that is why, so taking all this force and this exactly, then taking moment about I, sigma m about I equal to 0, and do all that. Since there is not much change except in the earlier case, equilibrium speed case, and now the only change is this Ms into G minus Fr, and therefore I shall get an expression that omega dash square is equal to 1 divided by h into bracket mv into G plus Ms into G minus Fr divided by 2 into 1 plus k, the whole thing divided by mv. So this is what is the speed when the sleeve tends to go down. When the sleeve tends to go down, this is the speed. Similarly, if I assume that sleeve tends to go up, the sleeve tends to go up, so that time the friction force is in the downward direction. The friction force is in the downward direction. That time the speed, instead of omega dash, I shall assume that it is mv omega double dash square into r. Let the speed of the governor be omega double dash. So that time the friction force is in the same direction as that of the weight of the sleeve, and that time the force is Ms into G plus Fr divided by 2. Though the sleeve has remained there only, and therefore if I calculate now, omega double dash square is equal to 1 by h into bracket mv into G plus Ms into G plus Fr divided by 2 into 1 plus k, the whole thing divided by mv. So please remember here, the sleeve is in the same position. The sleeve has not changed its position. Okay, between the speeds omega dash and omega double dash. Okay. I hope you have understood this, because I would like to make use of some space of the board here now, and I shall rub some things. Okay, I would like to. So imagine a thermometer. Okay, it is supposed to measure the temperature. Okay, say the temperature right now, say, is about 30 degrees Celsius. So what the thermometer is supposed to indicate, for every change in the temperature, it is supposed to indicate, it is supposed to respond, and its duty is that the function of the temperature thermometer is to indicate what is the exact temperature. Okay, suppose there is a small change in temperature, say 30 degrees, and now it has become another 0.5 degrees centigrade more. So the thermometer is supposed to indicate 30.5, but it is not doing it. It is indicating still 30 degrees centigrade. What do we call it? We say that thermometer is insensitive for the change in the temperature. A similar thing is happening here in our governor also. The governor is in this position. Okay, the sleeve movement, the movement of the sleeve is very, very important for maintaining the constant speed. If the sleeve does not move at all, even if the speed changes, then what do we call it? We say that governor is insensitive. You have seen here, because of the friction, even if the speed goes to omega dash, which we have got it as, say, one speed omega dash, even if the speed goes below omega, that is omega dash, then also governor is not changing its position. And even if the speed goes to omega double dash, then also the sleeve has not changed the position. If the speed goes more than omega double dash, then the sleeve will move. Similarly, if the speed goes below omega dash, then only the sleeve will move. Between omega dash and omega double dash, the sleeve is not moving at all. Omega dash to omega double dash, no change in sleeve position. No change in sleeve position, and therefore we say that it is insensitive. Governor is insensitive in this position. During this range of speed, the governor is insensitive. Governor doesn't do any work at all. Its intended work it is not doing, and therefore we say that governor at every position. Please remember whatever I have shown now. This is true with every position. Okay, at this position, the speed is omega when friction is not there. If friction is there, then it will remain in the same position even if the speed goes down up to omega dash. The governor sleeve will remain in the same position even if the speed increases up to omega double dash. So between omega dash and omega double dash, the governor is insensitive. Therefore, there is something called as, I can calculate what is the coefficient of insensitivity depending upon the governor. This is calculated by COI, coefficient of insensitivity is equal to omega double dash minus omega dash divided by omega. This is called as coefficient of insensitivity. This should be as small as possible so that for very effective working of the governor. Okay, so what is the effect of the friction? The effect of friction on a governor, okay, is friction makes governor insensitive, or it doesn't make the governor to function its duty. Okay, for every position, certain range of speed. So therefore, governor doesn't do its duty because of the friction. And this friction, if it is smaller and smaller, then this becomes coefficient of insensitivity becomes smaller and smaller. That is how we can make governor more and more effective. So as I said, so this whatever the analysis I have shown, omega dash to omega double dash, omega dash, omega double dash. What is omega dash? Omega dash is the speed of the governor at some position of the sleeve when the governor sleeve tends to go down. Similarly, omega double dash is the maximum speed of the governor at the same position of the sleeve. So please remember, as I said, this is true for a position, for every position of the sleeve. And what is the position of the sleeve when the governor ball is running? Governor is running at its lowest speed. Okay, please remember every governor shall have something what is called as lowest position and highest position. Lowest position. When the governor is sleeve is the lowest position. So lowest position of sleeve. Okay, so please remember these RCU, NU, NL, RCL, NS and MB, they remain same. Okay, then what are the different? Alpha minimum, then what is called as beta minimum. Minimum corresponds to the lowest position. remember H minimum is more than H maximum. I mean, when the sleeve is at the topmost position, H value is smaller than this. Okay, but I still call it as H minimum. H minimum is not the minimum value of the H. Minimum H minimum means the value of H when the sleeve is at its bottommost position. Okay, these are the values corresponding to equilibrium position of sleeve at its bottommost position, at its lowest position. Similarly, I have the same value of alpha minimum. The sleeve has not changed its position. R minimum also same. But omega minimum is not omega minimum now. I shall take omega minimum dash. In the lowest position, when the sleeve tends to move down, this also is same. H minimum. This is when we take friction. When friction FR tends to go up or is in the upward direction. Similarly, alpha minimum, beta minimum, R minimum, then omega maximum, sorry, not maximum, omega minimum double dash, comma H minimum. So this is when FR is in the downward direction. This corresponds, these are the different notations what you use when the sleeve is in the lowest position. Similarly, you have a similar set, topmost position of sleeve. Okay, so first set, when you don't consider the friction, what you will have? You will have what is called as alpha maximum, then you have what is called as beta maximum, then the radius also is maximum, then I have what is called as omega maximum, then you have what is called as H maximum. Please remember, H maximum value is less than H minimum value. H maximum corresponds to height of the governor when the sleeve is at its topmost position. So this is if friction force is 0, if FR, the friction is 0, in that case these are the notations. Similarly, alpha maximum, then beta maximum, then R maximum, then omega maximum dash and H maximum. This is if FR is in the upward direction. Similarly, alpha maximum, beta maximum, then R maximum, then omega maximum double dash and H maximum. This is equal to when this is if FR is in the downward direction. Okay, so you are normally asked to find out if the sleeve is in the bottommost position and the topmost position, then find out what are the speeds, and finally you are asked to find out what is called as the range of speed. A very common term which is normally asked. A range of speed considering friction. Taking friction, taking FR, taking friction force into account, what is the range of speed? So find out, okay, what is the maximum speed and what is the minimum speed. So minimum speed will occur whenever the sleeve is at the lowest position. So at the lowest position of the sleeve you have three speeds, what is called as omega minimum dash and omega minimum double dash. Omega minimum is always between these two, omega minimum dash and omega minimum double dash. So omega minimum dash is the lowest speed and the maximum speed will occur when the sleeve is at the topmost position, and what is that speed? That is nothing but omega maximum double dash. The range of speed taking friction into account is omega minimum dash to omega maximum double dash. Sometimes some people, some books call range of speed as the difference between the maximum speed and the minimum speed. Even if you write the range of speed, this lowest speed to maximum speed, and then subtract the two, and then write down what is it. So many radians per second is this. And if you don't take friction into account, without friction, what is the range of speed? So without friction, what is the minimum speed? That again at the lowest position of the speed. When you don't take friction into account, what is the speed here? That is omega minimum. This is the lowest speed. So that is omega minimum. And what is the highest speed? That is omega maximum. So omega minimum to omega maximum is the range of speed of the governor without taking friction into account. Similarly, if you take friction into account, then it is omega minimum dash to omega maximum double dash. Okay? Then I wish you to go back to the same formula, and then so what is omega minimum dash? If at all I want to write down what is omega minimum dash, I would like to write down. I just say omega minimum dash square is equal to 1 by h into, this is nothing but mb into g plus ms into g minus ff divided by 2 into 1 plus k, the whole thing divided by mb. Please remember, all these questions, the h is nothing but h minimum. And this will not change, this will not change, this k also corresponds to k minimum. What is k minimum? Tan beta minimum divided by tan alpha minimum. This is how the formula will change. Okay, so similarly, what is omega maximum double dash? That is equal to omega maximum double dash square is equal to 1 upon h maximum mb into g plus ms into g plus ff plus friction force divided by 2 into 1 plus k maximum. What is k maximum? Tan beta maximum divided by tan alpha maximum. Okay, so that is how you can find out what is omega minimum dash, omega maximum double dash. That is how you can find out what is the range of speed. Okay, so with this, the Porter Governor discussion is over, and you can solve any problem on Porter Governor now. And if you have any doubt, you can definitely come back to me and send your query. I shall definitely will be very happy to reply to it. Thank you.